Annyeonghaseyo. Welcome back to Automatic Control Systems lecture. In the last class, we discussed on time domain analysis of second order systems. In this week, we will continue with the same second order system analysis. We would like to analyze the step response of second order systems. So, this is week 5 part 2, time domain analysis part 3. So, we will be only focusing on step response of second order system. Recap from our last week, we discussed on the undamped response of standard second order system, and we saw in the undamped that we get y of t is equal to 1 minus cos omega n t. So, when damping is 0, we get pure oscillations. So, in the same way, we also analyzed on the undamped system response. When eta is less than 1, the system provides damping, but we will have exponential term and a sine wave. So, when we have an exponential term and a sine wave, our response will be a attenuating sinusoidal. So, you have a sinusoidal wave where the value is decreasing with time. So, when you multiply an exponential term, that means when you have a sine wave and then multiply with an exponential term like e power minus a t, and let us say this is sin omega t, you get resultant in a sinusoid. So, this is what we call damped sinusoidal. This is the response you observe in many mechanical systems like suspension systems. Because of the damping, we have this kind of system. So, this can be easily as e power exponential t minus t, and you multiply with the sine wave, which eventually gives you a decreasing or value of the sinusoid will decrease with time. When t tends to infinity, it approaches 0. So, this is natural undamped response. So, we have seen in the last class how do we actually get the expression. You can use this one, substitute the values and use inverse transform. This is fairly simple, and I expect the students to evaluate themselves and try to get the solution. So, we analyze for undamped system and underdamped system. The third one is critically damped system. Critically damped systems are also quite nice, where eta equal to 1. So, when eta equal to 1, the roots here are minus omega n and minus omega n. The roots are equal roots, both are real and equal. So, when we actually analyze the system, we get omega n square by s into s plus omega n square, and if we inverse Laplace transform, I get y of t is equal to 1 minus e power omega n t plus omega n t. What you see here, there is no sine term, it is just an exponential decrease. So, undamped systems actually provide something interesting. So, you have a system here, and then if this is a step input, what you get is something like this. So, undamped system does not give you any oscillations, it will just give you a simple exponential decay. This is very difficult to physically develop damping systems or suspension systems with this kind of critically damped engineering difficulties. So, we do have such kind of systems. For example, it is not exactly equal to 1, but close to 1. So, when eta is becomes 0.98, 0.91, so there will be very small oscillations and almost equal to 1. One such system, critically damped system, is airplane suspension system. When airplane touch the runway, there is a huge amount of force, and then the suspension will only come up slowly. There is no oscillations, because aircraft suspension does not have oscillation. If it has oscillation, it can structurally affect the aircraft. So, that is the reason the damping value of the aircraft suspension is almost close to 1, but not exactly equal to 1. So, critically damped systems are quite useful for difficult to build and only for expensive systems and important applications. We developed critically damping. Most systems have 0.7, 0.8, 0.9 range. Okay. Then the last part, we have over damped response. So, over damped response is eta greater than 1. It is very difficult to do and not common in many applications. So, if you are actually looking through the analysis part, if you take the transfer function for the over damped system, we can just simply do approximations. We get y of t is equal to 1 minus e become is the response will be similar to first order system, and we are not really concerned about overdamped systems because practically it is very difficult to build such systems. So, of all the 4 varieties, undamped systems, underdamped systems, critically damped or overdamped, almost all the systems are undamped systems. So, we rarely have critically damped system, maybe 1% of the system. 99% of the systems are undamped system. So, our next analysis, all our controller design, all our developments are generally for undamped systems, although sometimes we focus on critically damped systems, but it is quite uncommon. So, that is how the analysis for a step response is. Now, in this slide, following slide, I am going to actually show you how the damping affects the response of the standard second order system. This diagram is quite useful because if you see here, first one is eta greater than 1, the poles are on the real axis on the negative side. So, over damped system, and the response you see that it is like an exponentially growing function, it goes to 1. This is for eta greater than 1 over damped system. That is what we saw in the analysis. So, then the second one we have eta equal to 1. When I say eta equal to 1, we call critically damped systems. As I told you, aircraft systems have this kind of critically damping, close to, not exactly critical damping, but close to critical damping. So, these roots are equal, real and equal on the same location. You see that the roots are also in the imaginary plane, you can see they both are in the real axis on the negative side. This is what called critically damped. And then the most common form, we have the third one for eta less than 1. So, when eta is 0 less than 1, we see for eta less than 1 you have this exponentially decreasing sinusoid. So, damped sinusoid. This is the effect when I have a sinusoidal term with an e power at, what we get is an exponential decreasing term. This term is dependent on damping. If damping is higher, attenuation rate is faster. If damping is lower, the sinusoidal takes a long time to get to 1 value. So, that is for 0 less than eta equal to 1. When damping equal to 0, no damping. Let us say, imagine you are riding on a bicycle and it has a spring, no damping. If you hit something, your cycle will be moving. It never stops. The damping, for example, in old generation cars, if you actually ride a 1940, 1950, 1960 cars, their damping is not so good. So, what you see is when they actually hit a hump, the car still move nicely. So, you will enjoy. So, the damping is lower, but when damping is 0, once you actually hit something, your spring has no energy loss. So, it will be moving for the rest of your life. So, that is the problem. So, that is without damping equal to 0. For 0 less than, for eta in the negative side, the value exponentially increases and the system is unstable. When the poles cross the real axis, the system becomes unstable. Okay, until here is what we called stable systems. After that, when the poles are all on the, we call these roots, poles, these poles are on the left hand side, the system is stable. When the poles move to the right hand side, the system becomes unstable. So, what we are looking at, these poles should never cross the right hand side. If the poles move to the right hand side, game over, the system becomes unstable. But when the poles are on the imaginary axis, we call the systems marginally stable. The stability we are going to work in the later classes, we are going to exclusively focus on stability. Stability is so important topic. And then if you see here, the poles are on the right hand side, then becomes the value increases with time. It is like a bomb that is ready to explode, the energy is always increasing. So, if the system energy is increasing with time, the system is unstable system. If the energy is decreasing with time or becomes a constant, we can say the systems are stable. Stability is a different concept, we are going to discuss on stability in the later class. Now, let us compare the unit step responses for underdamped systems. As I told you, we are going to exclusively focus on underdamped systems. Underdamped systems form the backbone of our engineering development. So, every system we develop in real applications are underdamped systems. If you compare here, if you see this diagram here, the unit responses for various values of eta, it's quite interesting because a unit step is applied to the system. For example, I have different values of damping. When eta equal to 0.1, I get a big overshoot. My input is 1, but my step response is going to 1.7, means the output goes 70% over the actual input. This is what we call overshoot. This is what we call overshoot. These overshoots are not desirable. We don't want overshoots. I want the output to be 1, I am getting 1.7. It may be dangerous as well. So, what happens if we increase the damping? When damping becomes 0.2, the overshoot decreases. That means the sinusoidal amplitude. So, then eta is equal to 0.4, 0.5, 0.6. As the damping is increasing, quite interestingly, as the damping is increasing, the overshoot is decreasing, the sinusoidal value. That means if you are damping, your exponential value increases, this amplitude and the convergence, rate of convergence also, that means the rate of the value decreasing exponentially also increases. When eta equal to 0.7, what you can see is you get almost 5% overshoot. When equal to 0.8, you get 0.3% overshoot. When eta equal to 1, there is no overshoot. When eta equal to 1.5, which are impractical. So, eta greater than 1 are not practical, means it is impossible to achieve in real world. In real world applications, we can't have eta greater than 1. So, all our interesting region, so our major region of our analysis is eta equal to 0.6 to 0.7. Now, coming to here, practical applications, most desirable eta is from 0.6 to 0.9. So, most applications, engineering applications, have eta 0.6 to 0.9. So, if it is less than 0.6, you get higher overshoots. Most applications 0.75, 0.85, most of applications are here. 0.9 is on the higher side, 0.6 on the slightly lower side, 0.75 to 0.85 are good damping. So, if you see the diagram here, 0.75 is around 5%. So, most applications, when you are as a control engineer, you try to have a damping equal to 0.7, 0.75, 0.8 something. So, that gives us a good performance. If your system is having 0.7, 0.8, then there is a good damping effect and the output will be attractive. That means the output does not really cross the step value. So, that is one important aspect of our step response, that is the effect of eta on the step response. If your damping changes, performance changes. If damping changes, location of roots change. That means I can clearly relate these two to two things. That means you have this complex plane, right, these roots. When these two roots location change, damping changes. When these two roots are here, you get different head. This equal to eta is equal to 0.5, let us say is equal to 0.6. So, different eta, different location of the poles, and the same way we have different properties of the system. So, the linkage is quite interesting. That means, if you change the eta, the step response changes, properties change. If eta is changed, the location of the poles also change. So, this is an important connection. If you really understand how the characteristic equation, how the poles, how the roots change, how the properties change, and how finally the time domain response changes. This is the understanding that should help you to really move forward the control engineering. The next, we are going to move into the unit impulse response of second order systems. Until now, we have gone through the step response of second order systems. Then the impulse response. Are we going to study ramp? No. We are going to only focus on step response and impulse response. Of these both, step response is very important. So, the student should really work on step response characteristics. Impulse response is not so important from the time domain analysis point of view, but however, we just try to understand how the impulse response work for second order systems. The unit impulse response of a standard second order system is given by this one. So, if you see here, impulse is quite interesting input. Impulse has a unit value at t equal to 0 and it does not have any value after t greater than 0. So, the frequency domain, when we Laplace transform an impulse, we get R of s equal to 1. Output is equal to the transfer function. So, that is why transfer function is also a impulse response of the system. So, R of s equal to 1. Case 1, we have undamped oscillation, eta equal to 0. S1 S2 is plus or minus j omega n. So, y of s will be omega n sin omega n t. So, if a system does not have any damping and you apply an impulse, it will just result in oscillations. So, whether it is a step or an impulse, if you provide any input for an undamped system, you just get oscillations. Undamped is like a simple spring. If you press something, it oscillates. Next, as important, most important is undamped systems. So, for an undamped systems, if you analyze the roots for the transfer function y of s, if you inverse Laplace transform, you get into omega n into 1 minus eta square e power minus omega n into sin term. So, this expression is slightly similar, but slightly different to step response. Still, it is also an attenuating sinusoid. So, for undamped systems, you get oscillations. For underdamped systems, I get attenuating sinusoid. So, for critically damped eta equal to 1, we get him similarly for the same roots. I get y of t is equal to omega n square e power minus omega n t. So, you also get an exponentially decreasing similar. Overdamped systems for eta greater than 1, if you take the roots, the two different roots, and I get y of t, you get e power minus beta 1 omega n t minus e power beta 2 omega n t. So, you get this one, this also has like a similar to, but the response is also like an exponential decreasing function. So, if we try to compare with the step response, the behavior patterns are similar, but the actual profile will be slightly different. So, now if you try to compare the impulse response for various locations on the complex plane. So, what is provided here, this is a complex plane, and when the pole locations are in different places, you will get different response. If the poles are on the left hand side, stable system. So, for a stable system, you see the output, although it is on the left hand side, the output decreases and catch up with the value. When the poles are on the imaginary axis, as I told you, it is no damping. So, it only results in oscillations. But when the poles are on the right hand side, the amplitude starts increasing, unstable systems. When we have in the left hand side, the system value is decreasing, unstable system. So, this is in line with whatever we discussed for the step response as well. So, students need not worry about unit impulse response, it is just for knowledge sake only, but more theoretical value is your second order system. So, you should rather focus on step response system and most important underdamped system. You need to derive this one, try to understand these two aspects as well. So, that is about our unit impulse response of second order systems. Now, the other part is time domain analysis. So, in a time domain analysis, what we are trying to do is we are going to expand on second order systems, step response characteristics. So, what we are trying to see here is for underdamped system. For an underdamped standard second order systems for eta less than 1, we have this time response. If you see this graph, you have these various values of TR, TP, TS, TD, MP, all these are provided. These are very important parameters and these properties are dependent on the individual characteristics of the system. If you remember our characteristic equation S square plus 2 eta omega ns plus omega n square equal to 0, we have two parameters here, one is eta, omega n. So, these two parameters define a system. So, when these two changes, location of roots change, properties change. Now, this is important because based on the step response characteristics, we can understand how fast a system can respond to an input, how fast it can go to the final value, and also we will also understand how quickly it can settle into the final value. This is various indexes or various properties. The first one, if we expand this one, what we see is what we are looking at is a rise time, peak time, TR, settling time. So, TR is called rise time, the time taken for the signal to go from 0 to 1 for the timing. This is what we call TR. Peak time is the time period at the first peak. So, TS is the time period at the first peak, and TS is what we call settling time, when the signal value goes within the 0.05, that means 5% or 2%. That means when the signal is oscillating, how quickly the value can become like within 5% value of your input. So, this is what we call settling time. And then peak time, this first peak is the maximum value, because this is an attenuating sinusoid, the value of the sinusoid decreases with time. And then MP is what we call overshoot, peak maximum overshoot. This overshoot is what is the value above the 1, because we apply input 1, we get MP value. So, the overshoot value depends on damping. If we remember our earlier slides, if we change your damping, your overshoot changes. So, we are trying to find various values of this one. So, what we are trying to understand here is rise time, peak time, settling time, maximum overshoot, and we call also TD, that is not important, that is 50% level. So, our focus will be on identifying these values for any system. So, if a system is provided like S square plus eta omega n plus omega n square, if the system parameters are provided, I want to find the properties of my step response. That means, I want to find what is my rise time, what is my peak time, what is my settling time, what is my maximum overshoot, and all this one. This we can actually use our expression y of t is equal to this one. If you actually closely look at our expression here, y of t is equal to 1 minus e power omega n t by root of 1 minus eta square sin of omega n into 1 minus eta square plus t plus theta. This is quite interesting, because if you try to look at this expression, we have y of t is equal to 1 minus some e power exponential term eta omega n t, and then we have 1 minus eta square, and then a sine term, and then you have omega n into 1 minus eta square t plus theta. So, this is a sine function, this is an exponential decreasing function. So, when you multiply these together, you have a damped sinusoid. So, that is why you have the response here into this one, the y of t, the MP value decreasing with time. So, based on this, we can easily find various overshoot, various peak time, rise time values from the same expression. So, our time response indices, what we are going to focus is rise time, peak time, maximum overshoot, settling time, steady state error. These performance indices are derived from the unit step response of second order system. So, we are going to use this standard undamped system and then trying to find all these indices. Another important aspect is we are going to mainly focus on underdamped system. That means, when eta is less than 1. So, all our focus is on the systems for eta equal to 1. So, this can be only used for eta less than 1, very important. So, we are only going to study the case for eta less than 1. So, for eta less than 1, for the underdamped system, we are trying to formulate all these expressions. Now, coming to this here, The performance indices are derived from the unit step response of the standard second order system. Y of t is equal to this expression, and for simpler analysis we are going to use tan theta sin theta as well. From the expression from earlier we have cos theta is equal to eta, that means sin theta is equal to 1 minus eta square, and tan theta is equal to tan inverse of 1 minus eta square by eta. So, this forms our background for actually calculating rise time, peak time, and this one. Going to this expression, going to this graph, if you are trying to understand how do you get rise time, that means this is rise time is when y of t equal to 1, am I right? So, when t is equal to tr, y of t is equal to 1. Can you actually compare from here? When t is equal to tr, y of t will becomes 1. So, equate y of t equal to 1 and t equal to tr, and then we can use this expression to find expression for tr. So, that is another aspect of how we are actually going to calculate for all the values of the expressions. So, we can actually substitute these values, that is how we are going to actually find the values for rise time. So, here substitute y of t is equal to tr, that means y of tr is equal to 1 value, and then we can actually go with the rise time expression. So, from 1, when y of t reaches 1 for the first time, tr is equal to, tr is 0.0 to 100 for undamped system. So, y of tr equal to 1, substitute y of tr equal to 1, and then we can actually calculate the value for the expression. So, this is one procedure of how we are actually going to study all the aspects of all the parameters of our second order system response. With this, I would like to complete this part of the lecture, and in the next class we will be continuing with the identifying the expressions for rise time, peak time, overshoot, and the rest of the parameters for underdamped second order systems. We will continue in the next slide. Thank you. This is the end of week 5 part 2. Kamsahamnida.